We have seen how to understand what is Cm alpha dot, what is Cmq, what is Cl alpha dot. You could very well appreciate the sign of Cmq is negative and Cm alpha dot also will be negative because alpha dot is coming because there is a lag in downwash primarily. So actually the tail at time t is C more angle of attack because the downwash is happening only at a time later than time t by Lt by u1. So that will also give a nose down moment. So Cmq and Cm alpha dot both are negative. Cmq and Cm alpha dot are less than 0. Okay. Now we come back to this perturbed force Fz equation. We have seen the Fz by du by u1. We have developed that expression, and that was given as this is q1s 2cl1 plus clu. We have done last lecture. We have done this also at steady state. This expression is this. Just I'm revising this. dfz by dq. If you see dfz by dq here, it will be what? Let us understand this. This is the expression I have written. It's very obvious for you. You know, fz, fza because of q will be what? That will be half rho v square s into clq into qc by 2u1, right? Only q, right? It's the partial derivative. This is c dcl by dqc by 2u1. So this is the value. So dfz a by dqc by 2u1 will be equal to nothing but q1. That's because it's evaluated at steady state. So this is remaining at q1 and then clq. Okay? q1, clq, and of course there is s. And that is exactly is this expression. Very simple, right? Similarly, if you want to find out, okay, let me see this. This is done. dfza by d alpha dot c by 2u1. So again, fz only because of alpha dot, holding others constant where because we are trying to find out partial derivative. So this will be half rho v square s cl alpha dot into alpha dot c by 2u1, right? So dfza by d alpha dot c by 2u1 will be nothing but q1, where this is evaluated as steady state. So half rho v square at steady state is q1 into s into cl alpha dot. Right? There is a slight mistake, if you could see that. You must understand this expression and this expression. What is the mistake? You could see here, please note down here. As far as number is concerned, q1 is clq, fine. But what we are trying to find out? dfza. And I have been telling you that z-axis is pointing downward and lift is upward. So this force will be towards lift direction, because if q is positive, the force is towards upward direction, but which is opposite to z. So I have to put a minus sign here for clq, right? Coming back to alpha dot, what is happening? Why alpha dot is coming? Because there is a delay in the downwash to come here because of vortices takes time. So actually it is having at time to more angle, right? So that will give a force positive upward, but z is downward. So I have to put a minus sign here. Please be careful about this. Although both of these derivatives will not make much of a difference in dynamic stability for most of the airplane, but we should be very clear about our convention. When I add fz bracket q means, do not get misled, this is for q perturbation. Okay? That means holding other perturbation to 0 because we want to find out partial derivative. Okay? So this sign is very important. Please develop this habit of asking yourself whether I am giving correct sign or not. Okay? So this is over, this is over, this is over, this is over, and this is over. So now I can easily expand fz using these expressions. Correct? Let us see what happens if I do that. You know the equation of motion is fz minus mg theta sine theta 1 is equal to m w dot minus q u1, right? We have to substitute fz using this expression and using the values or expression for all this term. For example, for dfz by du1, we will put minus q1s into 2cl1 plus clu, right? For dfz by d alpha, we will put minus q1s into cd1 plus cl alpha, like that. For dfz by dq also, we will put like clq into qc by 2u1. So if I do that, then I get equation m w dot minus q u1 is equal to minus mg theta sine theta 1, okay? So plus q1s into minus clu plus 2cl1, okay, into u by u1. Similarly, minus q1s into cl alpha plus cd1 into alpha. We're just substituting those values. Similarly, minus q1s cl alpha, very good. Then minus q1s clq into qc by 2u1. Similarly, minus q1s cl alpha dot into alpha dot c by 2u1, and then minus q1s cl delta e into delta e. So that becomes my second equation. But we need not get disturbed by seeing this equation. I'm sure you understand. Now you are clear about each and every term of this expression. W is the perturbed W dot. Q is the perturbed pitch rate. Theta is the perturbed pitch angle. U1 is the steady state velocity. CLU you know, CL1 you know. CL1 means lift equal to weight. From there you find CL, because we have assumed cruise to be our equilibrium. We are giving the disturbances. We are giving the small disturbance, to be more precise, about cruise, right? So this expression is known to you. So this is fantastic. So one equation you have got through fx equal to, another you got through fz. Fx is basically forces along the x direction. Fz is plunging this direction. Now what is left is a moment equation. Okay, so we'll finish the moment part now. So you have seen we are trying to develop equation of motion, perturbed equation of motion for longitudinal case. For longitudinal case, where we have already seen the equation along x-axis has been completed, along z-axis has been completed, along x is this, along z is plunging. Now what is remaining is pitching, because we know we are talking about longitudinal perturbation. That is, in the perturbation, this aircraft will do like this. In the process, it will go up and down, and their velocity along x also will reduce. We are not talking about any lateral motion, because we are talking about longitudinal case. We are assuming that the aircraft remains in the vertical plane, okay? And that is possible only when you give small disturbances, right? So the last equation was pitching moment. M is equal to Iyy q dot, okay? And we are trying to find out how this moment can be modeled, like how fx, fz were modeled in terms of motion and control variables. Delta means control. So similarly, we want to model pitching moment, perturbed pitching moment in terms of motion variable and control variable. Very simple. Now you are expert. M you write function of alpha, or let's say u by u1, alpha q alpha dot delta e. Okay? What is next? So m you write as dm by du by u1 into u by u1 plus dm by d alpha into alpha plus dm by dqc by 2u1 into qc by 2u1, then dm by d alpha dot c by 2u1 into alpha dot c by 2u1 plus dm by d delta E into delta E. Okay, these are the equation for, or this is the expression for postulating pitching moment, which is a perturbed pitching moment, and assumption is this pitching moment will depend upon perturbed u, alpha q, alpha dot delta E. For small disturbance for a conventional airplane, this is okay. I repeatedly say, as we are going for a high performance airplane, the argument may go on changing. There may be delta E dot, there could be alpha q, so many things may happen, right? But we are taking simple things to understand the basic principles, basic techniques, and how do I use those equations to get basic parameters. That is more important for us. So let us understand, we have to find out this dm by du by u1, this will be at steady state. Okay, so let us first find out this dm by du by u1. So you know that moment will be, or I write moment will be equal to half rho u1 plus u, because we are trying to find for perturbed u. So what is the assumption? Is the airplane was moving with u1, and because of perturbation, this is u. Total velocity is now u plus u1. We are assuming again here that everything is linear, right? So this is half rho v square s into cm. Of course, there should be another length term, so c bar. So half rho v square s c bar into cm. So now we want to find out dm by du by u1. You know, technique is as simple as that. Half rho u1 square s and 1 plus u by u1 square. And here I write c bar here and cm. So this I can write in a better form. I write half s c bar into 1 plus u by u1 square into cm. What I am trying to find out? dm by du by u1. So what I do? I write dm by du by u1. Nothing. First time I am doing, this is q infinity s c bar, and this is 2 into 1 plus u by u1 into cm plus q infinity s c bar into dcm by du by u1 into 1 plus u by u1 square. First, I am taking derivative with respect to u by u1. Is first this term, this 2 has come here, and then second is cm. Now, what is the understanding? This should be evaluated at steady state. And steady state, at steady state, you know, u is 0. Perturbed u is 0 at steady state. So what do I get? I get dm by du by u1 as q infinity s, 2 will be here, c bar into cm plus q infinity s c bar into dcm by du by u1. Okay, but since I am evaluating at steady state, not only I put u equal to 0, but also I should know the cm or q infinity is q1, dynamic pressure at steady state, cm1 at steady state, this becomes 1, and this is evaluated at steady state. Fine. What is cm1 for an airplane? Cm at steady state is how much? It will be 0. cm1 is 0, that is trim. Okay, then what is dm by du by u1 or dcm by? Okay, this is important. This term, dcm by, because this man goes at steady state, cm1 is 0. For cruise, that is the phase about which we are giving small disturbance, right? So this dcm by du1, I can write this as m1 into dcm by dm. You know how? You are all expert now. You have done it earlier also. I have divided here by A, divided here by A. A is the speed of sound. So this becomes dCm by dm, and u1 by A is m1, which comes here. Right? So now understand dCm by du by u1 is nothing but m1 dCm by dm. And this is very, very important parameter. This is extremely important parameter. What is dCm by dm? Remember, if this is the tail, right, the AC of the tail is somewhere here. It's a C by 4 for a subsonic speed, right? As we go supersonic, high speed, this AC goes backward. This dCm by dm is extremely important, and I was trying to explain that, you know, at low speed, the AC of the tail, this is tail, assume the CG is somewhere here of the aircraft, AC of the tail is here. As we increase the speed, go supersonic, the AC of the wing or AC of the tail moves backward. It tries to approach to around 50% of the chord, mean aerodynamic chord. So what is happening? As I am increasing the Mach number, this LT is going on increasing because AC of the tail is moving backward, right? So the distance from CG, which is LT, is increasing. That increase in LT will give additional moment, delta Cm, pitch down moment. And what will happen as I am trying to accelerate? If I don't understand this phenomena, as I have to accelerate to supersonic, there will be pitching moment and airplane will try to go like this. This is called tuck under phenomena. And a lot of accidents happen when we are not able to understand what is this phenomena, tuck under. This is clear? So dCm by dm is extremely important. You could see that as I am increasing my speed to supersonic, there's additional pitching moment, dCm, which is coming because the AC of the tail is moving backward, and this dCm by dm is negative. And it gives a pitch down moment, and hence the tuck under phenomena. So this is extremely important. We must evaluate this when you are trying to do analysis or dynamic stability, especially in supersonic Mach number. Okay, right? So what we have seen now, we have seen dm by du1 is nothing but, our aim was to find out dm by du by u1, and we have seen this is equal to q1 sc bar cm1 plus q1 sc into dcm by du by u1, and which is nothing but is m1 into dcm by dm. This is nothing but m1 into dcm by dm, and this is negative at supersonic speed. So that is the derivative dm by du by u1, and we know if the trim is at cruise, then cm1 definitely is 0. This is one term we have evaluated. Okay, now we have to evaluate. You please understand this derivation, then in one lecture you will write all the derivatives, neat and clean, and then put them into equation and get a nice equation. At this point, every derivative, note down, oh, this is the meaning of this is the physical significance of this. That is more important, okay? Don't get lost into all these big expressions. So, you have seen dm by du by u1, we have evaluated. So, dm by d alpha will be what? Very simple. You know that how to do it. M is half rho u1 square sc bar into cm. So we are talking about alpha derivative, right? So dm by d alpha will be q1 sc bar dcm by d alpha. Right? So that also we get. Now we want to find out dm by dqc bar by 2u1. Very simple. We will write this is q derivative. Okay. So m will be half rho u1 square sc bar into cmq into qc by 2u1. So dm by dqc by 2u1 will be equal to q1 because I'm evaluating at steady state. These are routine things now for you. So this is CMQ. Similarly, alpha dot derivative, m I will write as half rho u1 square s c bar into cm alpha dot c by 2 u1. So dm by d alpha dot c by 2 u1 will be equal to q1 s c bar cm alpha dot. Similarly, control derivative, if I want to find out delta derivative, elevator, so I will let m is equal to half rho u1 square s c bar cm delta e into delta e, right? So dm by d delta e at steady state will be q1, this is dynamic pressure at steady state, q1 s c bar cm delta e. q1 is the dynamic pressure at steady state. 1 means at steady state. So you see, very simple. You have all the expressions with you. dm by du1 you have dm by d alpha, you have dm by dq, dm by dqc by 2u1, you have dm by d alpha dot c by 2u1, dm by d delta e. And you also know how to estimate cm alpha dot, you know how to estimate cm delta e. We have written m is equal to dm by du by u1 into u by u1 plus dm by d alpha into alpha plus dm by dqc by 2u1 into qc by 2u1 plus dm by d alpha dot c by 2u1 into alpha dot c by 2u1 plus dm by d delta e into delta e. Okay? We have developed expressions for all these derivatives. For example, if I take dm by d delta e, which is nothing but q1 s c bar cm delta e. And we know the expression of cm delta e. You might have seen initial lecture. You will have expression for cm delta e. You see dm by delta e is q1 s c bar cm delta e, and you have already done that cm delta e is nothing but minus cl alpha tail into vh neta t into tau. So what is the message? Given the configuration of the airplane and given the flight regime, the altitude, the speed regime, I can easily find these derivatives which are evaluated at steady state. What I need information, what is that dynamic pressure at which the airplane is at trim? S and C are from the aircraft. For Cm delta E, what I want? CL alpha tail, I know. Vs tail volume ratio, I know. Neta T, maybe 0.91, and tau also I know. So all these values, for example, for Cm alpha dot also you have shown you the expression. I can find Cm alpha dot, I can find Cmq. All the things I can find out. In a nutshell, what I'm saying, all the expression or values of these derivatives will be known. Okay, right? And once I know that, I know this is equal to Iyy q dot, right? M equal to Iyy q dot. So I can easily write the equation q dot in the form q dot equal to mu into u plus m alpha into alpha plus mq into q plus m alpha dot into alpha dot plus m delta E into delta E. Like we have written for the x direction. For z direction also we'll write like that. And then once we form the equation, we'll be actually solving them to get what exactly we are looking for. Okay? What we are trying to do is we'll develop q dot. We have already developed u dot. We have already developed w dot. In terms of dimensional derivative, this is mu, m alpha, they are dimensional derivatives. I have shown similar thing for the other cases, dimensional derivatives. So for example, m alpha is dimensional, but cm alpha is non-dimensional. Once I write these three equations like this, then I know how to solve this equation for a different control input, delta E, and see their response and check whether the airplane is dynamically stable or not. So that will be our next task. So far, we struggled, we worked very hard to develop this expression and explicitly bringing out what are these expressions, what are these partial derivatives, and what are the important points you should understand as a designer, right? So next class, we'll summarize them, we'll synthesize them, and get a neat equation on how to solve it to get stability characteristics. At this point, I must tell you, if you have time, just go through Laplace transform, right? Okay, that will help. Thank you.